Because adjust, otherwise I will stop. Can you listen at length? So I won't use this because it will only create trouble. I believe. Let me see. Child. See, one problem is that you are so far off. I don't know whether you will be able to read, you will be able to make out anything. What I will show. Then you know, zoom. Okay. See, I will give you the basics of global positioning system. Okay, what is called the GPS. Or you are broken. If you can't listen to me, please tell me. Right? Right. So it's all right. তাকে করে আমি কি করি? এটা করো। লাইট করা দরকার নেই, পরের থেকে তাতে করে লোকে আরো বুঝতে পারবে না। না আমি শিক্ষক না, তাহলে আমি অ্যাডজাস্ট করতে পারি। So the global positioning system is a part of something what we now call Global Navigation Satellite System, which is GNSS. Okay, because when the GPS was developed by the United States Department of Defense, that was the only system, okay, that used to offer navigation, satellite-based navigation and positioning. But after GPS, can this be raised from there? You can make it out, okay? Other systems have come up. Can I have them become different color? I will tell you also logging. Oh yes, sorry, yes. But then lot of other things came, like the GLONASS, which is a Russian system, and then came Galileo, and Compass and many others. Okay, other systems came, developed by different nations, and now all these were put under an umbrella term, which is GNSS. Okay, which is Global Navigation Satellite System. So some of the GNSS acronyms, okay. So the most important thing is the GNSS, because this incorporates everything, right? Like when you call life science, it means physiology, it means botany, it means zoology, everything comes under the purview of life science. So now GNSS is a term in which all these satellite-based navigation satellite systems are incorporated. Okay. We all are familiar with GNSS or GPS, as it is popularly called, because people don't use GNSS as much. Now you have your smartphones, you can use Google Map, and you can always locate your positions, and that is GNSS only. everything, whatever you are seeing in the map, and you can share your location. You can share location with your friends, with your family. You can see where is your mother or father or sister or brother or friend in Google Map. Everything is controlled, located by GPS. So here, today, we shall learn in very simple terms how this positioning is achieved. Okay. Now the thing is, I don't have any PowerPoint projection. I will just go there, find something, out of a lot of figures, and you will have to bear with me, okay, for that. Now, first, we need to learn something, because some of you are not from the art science discipline, right? Or all are from art science. I don't know, geography, geography, all of them. No. Everyone is there. Okay. Now see, if you want to define my position in respect to this room, what is best thing to do? We can go like this. This is x-axis, this is y-axis, this is z-axis, right? And if this x-axis and y-axis, when I stand here, my y becomes 0. If I stand here, my z becomes 0. If I stand up, my z becomes a few centimeters. And try to understand that based on this x, y, whatever it is, and z, we can define everything in this college. We can define anything which is beyond that to be minus, up, down, and for that matter, using this frame of reference, we can define anything in the universe, not universe, at least the earth. Okay, anywhere. This is my origin. Okay, so to learn about the x, y, z of one person or one element, we need to have a three-dimensional coordinate on the basis of that. So the GPS works on the basis of such an coordinate. The center of which is at the center of the earth, right? Now, but we are on the top of the earth, not on the center of the earth. So there are some very basic relations that we need to know. How do I? Is there a tasker somewhere? I mean a whiteboard. Yes. Hey, one of these is a permanent marker. This is a permanent marker. The GPS is gets permanent feature. See, this is Earth. Okay. And the radius is roughly 6400 kilometer. Right. And I think it is 6370 or something like that. You can Google and find. But I'm taking as 6400. Better than me. It's around 6400. So now, to get the circumference, we can easily use 2 pi as a reference point to get the circumference. Right. So in that case, 2 pi r will be 6400 kilometers. Why have put this off? Oh, these are the put off. Can we have the lights? No, we can have some natural light. So this will have 360 degrees, right? And see, 1 degree has got 60 minutes. And 1 minute of course has 60 seconds, right? Apart from the linear distance in art science, there is another type of distance which we call arc distance, right? That means the distance covered along the circumference. So that's the curvature. Any aeroplane, although you can show it to the point of the map going straight, it can't, of course. It would follow a curvature. Okay? And that curvature would be twofold. Because if you just press the string, you will find that if you just slightly go either to the east or to the west, you will take a north south line or whatever. But these are arc distance, right? Now, so there would be an arc minute and an arc second. Sir, can we just put this thing on the telephone? You may have heard of a term called nautical mile, which is called knots. Knot means nautical mile per hour. If you go to any website that deals with tropical cyclones, you will find the wind speeds are given in knots. KNOT means nautical miles per hour. Now, what is nautical mile? Very simple. 1 nautical mile is 1 arc minute. Get my point? This is the radius. Okay. Now you shift it by just 1 minute. The distance here, of course, you are on the scale, is 1 nautical mile. Okay. Okay, that's right. And 1 nautical mile equals 1.852 meters. That is 1.852 kilometers. So if you just get a news, the speed of a cyclone is 100 knots, then you will have to multiply 100 nautical miles with a factor of 1.82. That is, something like, so whatever will be that, and almost double the speed, okay, in meters. And so, many of you have heard about the topographical maps or the topo sheets, okay, and these topographical maps, they have latitudes and longitudes. One topographical map produced by Sir Walking, you can purchase it over the counter, and that you can use a topographical maps in that 50,000 scale, 150,000. That means 1 centimeter equal to 500 meters. Okay, it's 5 minutes by 5 minutes. Using this sort of conversion, you can find out what is the arc distance in meters, not in nautical miles, but in meters. Okay, you can find it out. I can't go into the very detail of this because the time is limited and we will have to go to this main stuff, which is the GNS or GPs. But you will understand something, try to understand. When you say a map has got say this is 15 minutes, arc distance and 15 minutes arc distance. So these are the difference of latitude, right? The latitudes are going like this and the longitudes are coming like this. Okay. Now try to understand one thing. The latitudes are all parallel, right? They are all parallel. But the longitudes they converge at the poles. So they are the largest difference at the equator. And there are no difference at the poles. Right? So when we talk about this arc minute or arc second, they have different meaning in the case of the latitudes and the longitudes. Because the latitudes are all parallel, this will hold. So length of a second will be same as everywhere. Okay. So this is the length of a second of latitude. That is a north-south distance. But this cannot be true for the east-west distance. Because say the difference of 1 degree of longitude will be this at the equator, but then it will be 0 at the poles. So we must, I won't go into the mix very detail, but we can use the function of cos. Cos 0 degree means 1, cos 90 degree means 0. So we can multiply this with cos to get the distance difference between the longitude and different latitudes. Okay, if we want to find out the distance between the longitude at 22 degree north and 22 degree south, so we will multiply it as a function of cos 22 degree. Try to understand, okay? And I would say that coordinator, I will give some materials to them because they won't get it anywhere very easily. So I will give it so they can use this. Okay. So try to, you will ask why you are saying all these things. Why these things are related with GNSS? Yes, there is relation. Because when we talk about GNSS, we talk about meters. Okay. Distance in meters. How far is that? How long is that? And what time it will take to reach there when we talk, use this in Google Map. So we are all the time converting these angular distances to linear. And to convert, because the surface of the earth, convert, we need to learn the basics, how this conversion is done, how the arc distances are changed to linear distances, right? Please remember this. Now, the next thing, important thing, is the frame of reference. Okay. Tell me, do you know about this, have you heard about the Great Trigonometrical Survey of the Survey of India, what is called the GTS? Have you heard of that? Any one of you who are sitting at the back, last bench? Do you know about GTS? The Great Trigonometrical Survey? Okay. So that was taken up by the Survey of India. Okay. From the start of the 19th century, right? And they have mapped the entire Indian subcontinent. Not mapped, they have measured by a process called triangulation. So what is that? See, first I separate these permanent markers. They are all banana is a common whiteboard, board. Yeah. See, this is a line, okay, and We know the orientation of this line is north. We know the orientation. And we measure it very precisely. Very precisely. Let that be something like 3,000 meters. And that has to be precise by millimeters, mind you. It's not easy, but you will have to do it. There's a way of doing it. Okay. And this thing is being done at the beginning of the 19th century. Okay. That is 1800 something. Once you learn this line very well, very correctly, orientation very correctly, then what you can do, there is an instrument called theodolite, which measures horizontal distance and vertical distance, right? These are called theodolites. And from that, using the theodolite, another point can be located. Say, a hilltop can be located here. What information is learned? That is a good thing. We have things in so many colors. Good. And what we learn? We know this angle and this angle, right? And similarly, another point can be located here, maybe another hilltop. And what is learned? This angle and this angle, right? So we have two triangles. And if we learn this, if we know this, then what other things can be found out? We can find out this distance, right? You can find out this distance and this distance and this distance. So, two unknown points can be plotted on the map because we know all the distances now. Okay, because we know that the triangle, the three angles of the triangle would be 190 degrees. By that, if we know this and this, we can find out the other. So similarly, once these 2 points are known, other 2 points can be found out. So in this way, a large section can be mapped for their horizontal distance as well as vertical distance from one another. Okay. Now see, entire Indian continent was mapped like this. Let me show you some images. So it was started from Madras, and this triangulation went on to cover the entire India, okay, and all the Himalayan peaks. So this means that the heights of the sea level at Madras were carried to the entire continent. So this is a great trigonometrical survey that was, and you can see it goes down to Burma on one side and to the Afghanistan border on the other side. Okay. So this was the exercise, right? The great trigonometrical survey. Why? Talking about all this, why is it important? One way you know Rani Rashmoni, who found out the altitude of the Everest. Everest, actually, the exact correct spelling is Everest, right? And if you go to south of India, they won't call George Everest, they will call George Everest, because that is the actual British spelling. Now, Rani Rashmoni was an Indian who were instrumental in calculating and finding out the height of the Mount Everest, right? And you can understand all these triangulations and all these measurements are being done by hand calculations, not by any calculator. Everything. And there were no photocopying machines. And the photography was also at the rudimentary stage. That had to be hand copied. So you can understand the extremely difficult thing that had to be done. I am showing this because just to show you how the things were made. All these lines were the baselines. This is written as the Calcutta baseline. The north was something called borrowing tower. Okay, I'll show you. And this was in the 4 billion. Okay, and many of you who are from Calcutta would recognize this. Okay, these are a place called close to Shinki Moor. And this is one of the great GPS towers. Great geometrical survey. Tower, what I am about. So all these points which you have seen, they are on these GPS towers. Because I will just explain it. Don't worry, I will complete it one and I will complete the basics of GPS. Don't worry. But this is very important. Okay. A scaffolding used to be made. So there was a bamboo and wooden scaffolding around it. With, if you go inside, there is no stair, nothing. This gives a very sturdy base of placing an instrument. Okay? And these instruments were called the great theodolites. Okay? If you go to Victoria Memorial, have you been any one of you inside the Victoria Memorial? Have you been? Family? This I have photographed inside the Victoria Memorial. This is one of the great theodolites. These are called the great theodolites. The vertical plate is 2 feet. We have seen theodolites, have you? Small instrument. Only this you can lift it. But it used to take 6 pole bearers, 3 front, 3 back. Because it used to be so heavy. And that had to be placed on top of those towers. And you know, North India, always busy. And there is saying you can't do it. You will have to do it during the winters. And it's all hazy, all haze. At that time also there were fogs. So they used to take measurements in the night. They used to light a fire on one of the towers. And another tower they used to place this. And see this. This is a lantern. A lantern, of course, not electric. This is a lantern burned by kerosene or something like that to see the the readings. Okay. So this is, and in the telescope you can see the telescope, right? See this one. So if you go to Victoria Memorial, just have a look at this great theodolite. Okay. And I have one image from the Survey of India itself that shows, I think, yes, that will give you an idea of the size. So you require 6 people to get this. Apart from achieving a very accurate points and across India, the Great Geometrical Survey also achieved another very, very important thing. It achieved or it deciphered the curvature of the earth. Okay? The curvature of the earth from Afghanistan to Burma and from Kashmir to Kanyakumari, right? 2 arcs. So from the arc you can find out the center. Of course, it's an ellipsoid. The earth is not spherical, it's ellipsoid. But you can find it out. I won't go into the details how you can find out. You can see in the internet. Now, why this was important? This was important to learn about that X, Y, and Z of every place. Unless you know this, see one thing. Can describe the earth geometrically, the geometry of earth? Can you describe it mathematically? See, this is impossible. Because think of the Himalayan mountain. Okay, ups and downs like that. It doesn't have to do that, right? It is there. No, I won't go into that because I will have to complete by one. Somebody else. No, but I will have to complete. One problem is, you know your room. If you go to a house, if I tell you, I would just like to have dinner or have lunch, you will have to direct me that way is the kitchen and that way is the dining hall. Since with the laptops are like that, everyone has their own laptop and they know where which thing is. But the problem is it's a new machine, so I will have to find out. So I will just type to do that here. Okay. How you on the theory? No. Yeah, you hyperbolic theory. Here you can see. And this will some also working. It can work, but you can see, you can understand that if you just go on zooming, you can see the complexity. So this is not possible to define mathematically. Then there is another thing. So this is the actual topography. Then there is another thing, which is a geoid. I don't know whether you have heard the name. Geoid is nothing but the sea level, okay? Geoid. So, the surface of the ocean, and you will have to pretend or imagine that beneath the land, ocean continues, right? And so we always have altitudes as meters above sea level. We call ASL above sea level, right? So this means if we want to know the altitude of this place Singur, then we will have to imagine that there is a sea beneath Singur, always not there, and it's the height above the sea level. And if you have followed the Great Geometrical Survey, they basically have carried the level of the sea to the height of the mountains. Okay, so it's above the sea level. Okay. Now the problem these sea levels are also not easy, not at all easy to define mathematically. Okay, why is that? You see. Okay. See, here is a good image to understand this. This is the map of the sea level, right? And this is minus 105 meters and is plus 85 meters. So it is close to 190 meters. Plus and minus. Imagine you are sailing from the Madras to say anywhere in South Africa, in any port. Okay? Or you are starting from Calcutta even. You understand this is India. Okay? So you go down and climb up 200 meters and 200 meters. Okay? Of course you can't understand that because this is thousands of kilometers. When you are flying, you are traveling some 24 to 25 kilometers above the level of the land. Okay, but that doesn't mean anything because you are covering 1,000 kilometers. You are covering 800 kilometers, 700 kilometers. And so, A, this 24 kilometers is nothing. So, it is also like that, and the trouble is that it is always changing because this sea level responds to gravity. And this, the inside the earth, the materials are shifting. So the gravity shifts, and so the sea level also shifts. So you cannot define the earth's surface mathematically easily, not easy. It's not impossible. It's so complex. And you even can't define the geoid above which your altitudes are calculated. That is also not easily defined. So you need to define a simple frame of reference which is called an ellipsoid, which will only have a semi-minor axis and semi-major axis. Okay. From that you can define an ellipsoid that will best fit the geoid. Okay, so we have three things: actual, geoid, and ellipsoid. When the survey of India found the curvature of the earth in the Indian subcontinent, they could easily find out the center of the earth. But that is best suitable to India. Similarly, during the same time, the Americans found out their center of earth, Russians find out their center of earth, Europeans found out their center of earth, Australia found their center of earth, these center of earth. Because they are all seeing a part of the road. You understand? It's like, you understand? Okay. So they were different. These are called, these ellipsoids which were defined, are called the local ellipsoids. After the satellites were started to orbit the Earth, okay, starting from the Sputnik, that was the first satellite went up. After that, 60s, okay, and then Gagarin went up, and then regular space flights were possible. We have now have countless, not countless, everything is accounted for. But I think thousands and thousands of satellites now we have in the Starlink and all. And if we take all satellites that ever existed, that number will definitely move to 4 digits, right? And these satellites, orbit based on what? Based on the center of the Earth. Now, this center of the Earth is what is called the globally defined center, and all other center of the Earth were locally defined center. Your GPS used a globally defined center. The center of an ellipsoid, the name of which is global. What is the name? Does anyone of you know? The center of the Earth that was defined, the ellipsoid that was defined by Survey of India is called the Everest ellipsoid. Now we use the ellipsoid, the semi-major axis were defined in 1956. We call it Everest 1956. So similarly, there is a global ellipsoid. Okay, let me just give you the name. Before I give you the name, let me just do something different. See, this is the Everest ellipsoid, the first defined in 1840. This is the semi-major axis and this is the semi-major axis, okay? And that is the flattening, 1 by 300, around 301. And that is the local ellipsoid. And the global ellipsoid, now all navigation systems they use is the WGS-80. That is the World Geodetic System 84. This name you should not forget. Okay, the World Geodetic System 84 that was defined in 1984, and the flattening is slightly different but significantly. So the center of the Earth of Everest and the center of the Earth of the W84 they differ by more than a kilometer. Okay, the old survey of India maps, they all used this Everest body. But your GPS, which is inside your phone, uses WSA. So if you take old maps and get the latitude and longitude and want to navigate using that latitude and longitude, that won't work. Okay, because these two things are different. So the map of the Everest ellipsoid, the latitude and longitude is different. So every place has got two different sets of latitude and longitude. One by Everest of the old topographical maps, and another by your GPS, which is inside your phone, and a new topographical maps. Now if you go to Survey of India, they will give you maps of open seas, which are what's your discipline? Yes. Emerald science, very good. But I think you know about these things. Yes, the open series maps are, this GPS compatible because they are using WS84. But old maps were Everest compatible. Okay. So please remember this, and doing so, let us now go to the basics of the GPS. So now you know about the triangulation, right? You know about the triangulation. What is triangulation? That is a very important concept here. Because this is in this course aims to achieve this. After 4 days, end of 5 days, this is the first day, then end of the 5 days, you are expected to appreciate the integration between different survey techniques for environmental studies into a single system where all data can come and become interchangeable. Okay, what are these GNSS which we will cover, or we are covering? Total station, okay, and electronic distance measurer. So this total station, you may just not take this, but this is the total station that will be displayed probably today by outbound. Is coming. GIS is the way how you represent a spatial data in computer, geographical information system, or geographical information science. Any spatial information, any spatial database representation is done by GIS. And then there is remote sensing. Okay, sorry, this is echo sounder. Sorry. this echo sounder. Total station will give you a very accurate Z, X, Y, Z on the land side. But if you want to go down in the water, you will have to use the XY from GNSS and Z in minus from echo sounder. Okay. And remote sensing, of course, will give you the image, satellite image, or remote sensing can give you altitudes. Remote sensing can give you a lot of stuff. Okay. Lot of. Starting from interferometric data, radar interferometric data, which can give you a precise measurement of subsidence of different, and then to heat sensors that will give you the altitude, temporal, and so many data. Mind-boggling thought will give you remote sensing. But all has to be integrated in single frame of reference so that you can use it interchangeably. You will have to get your GNSS data analysis. Total location microphone analysis, and everything should go to GIS to understand. That is the reason why you require a common frame of reference, which is achieved by a projection system called UTA, Universal Transverse Marketer. What is that projection? Projection is how you represent the round earth to the flat sheet of paper. There are many ways of doing it. Okay. I won't go into the detail. So I will only touch upon this UTA projection, which is very important for our transverse marketer projection, which is very important to learn here. The thing is quite not very difficult to understand. See, it is like this. It is like this. You put a cylinder of paper, okay, and you put the earth inside the cylinder, okay, and you put a light at the center, and so all these latitudes and longitudes will project on this paper. Get my point? Now you split the paper, keep it open. Now we have the map of the earth inside. Okay. So now that is what we call the marketed projection. And now you are using something called transverse marketed projection. Okay. Let me see. We have the photograph. Just a moment. Yes, this is it. So this is what I was meaning, okay, something like this. And now this is a marketer projection, and when you just put it like this, the transverse marketer projection. Okay. And now you are just revolving it every 6 degrees. Okay, it is like this. Say you put this cylinder at 0 degree and 180 degree. Get my point? Then you just slightly shift it 6 degrees. Then it becomes 6 degrees here on the other side, whatever it is. And like that. And when you complete doing this sort of rotation, you come with this. Okay. Get my point? So here, the entire world has got 60 zones, UTM zones, right? And you can understand, everything has got 6 degrees of difference. That means in this particular zone, say if you just zoom to West Bengal, so this is zone 45. That means the cylinder touches at the center. Here. And in zone 46, the cylinder touches at the center. Right? So we have different zones of UTM. Now most of the data which you download from the different sites, whether it is from India's ISRO, The name of the portal is called Bhumigi. And whether you download the data from USGS, the Art Explorer, or Glovis, or you download data of Sentinel satellite from a site called Copernicus, EESA, European Space Agency. They will give you the data in UTM. From this, or on the other day when you the hands-on training will be there on the GPS, it will be configured to UTM. What is the advantage? You know what is the advantage? UTM will measure every place from the distance from the equator. Distance from the equator. Okay. So this is the distance. That is called the northing. And from the start of the zone, which is called the easting. So using UTM, the easy thing is that you have, easting and northing, which are in meters, not in degrees. And using the Pythagorean, children, it's very easy. If you know the xy of this place, and if you know the xy of this place, then you know this. Here you know this. In a distance you can find out, and so using this. I don't have to give the explanation. As the square of this and this would be the value of this, so we can find out the distance between any two parts in meters, not in between seconds. Okay, so that is the advantage of that. Now, please remember this. Okay, so you can have latitudes and longitudes. You can do everything. You can have everything in meters. Northing and easting, which is meters. And if you have something in meters, it's very easy to calculate. It's very difficult to subtract 88 degree 77 or 88 degree 60 means 45.33 seconds, and from 89 degrees 39 means 13.66 seconds. Very difficult, but it's very easy to calculate this many meters to this many down to centimeters. Okay. Now, what are the GPS? GPS are basically something like a constellation. Okay, constellation like this. And this constellation would go like okay. So this is something we have. Go to that. Six orbits. Okay. 4 satellites in every orbit. Average distance is something like 12,000 kilometers. Okay. Almost circular orbits. And these are, so we have 24 satellites. Okay, 6 into 4, 24 satellites. And we are arranged in such a way that any given point of time, at a given point or at a given place, you have always 4 satellites visible. Minimum. Maximum 12. Okay, all the time, anytime. Minimum 4, maximum 12. More satellites you have, more accuracy of position. Now the question is, how the position is achieved? How GPS position is achieved? Okay. So, your smartphone has got a GPS receiver. What it receives? It receives signal. 2 types of signal. One type is called AC links. That means it knows. Remember, everything can be defined in the way of XYZ. And the center of the earth is GS84 ellipsoid. Okay. It knows at any given point of time, say now it is 4 minutes to 1. I think I can continue for another 10 minutes. Someone told that. Where is the program technique? Last কটা করে শেষ হবে? একটা থেকে দুটো। Oh yes, that means they are allowed me to continue for some time. Anyway, because I told you all these things, nobody else is going to tell you all these things. All these things, because unless you know the basics, how we used to measure, it is difficult to appreciate. You know, the great advance that is being made. So, if I ask you what's your name, you will say I will ask Nando. Okay. They would have gone out because they would buy for this person. His name is Rajesh. My name is Rajesh. Okay. So, all these satellites, their position at any given time is downloaded to this system. If you take a GPS receiver, which you will be seeing, first, when you first put it on, it takes some time. You know, it is called, it is being, you know, it is receiving the impedance at one point. Okay? And it is hitting up. Takes some time. Because first the GPS receiver here needs to know at any given point of time what are the X, Y, Z of all these satellites. So at 1 o'clock, where is satellite number 18? Where is satellite number 24? Where is satellite number 2? You should know all this. Okay? So once this is done, now it is primed to get the position. And it uses something like triangulation to do that. Okay? How? So this is a GPS satellite, but different satellites are different types. Okay? Now try to understand. Say we know the distance. I will tell you how the distance is known later. We know the distance. Say I am here, I am the unknown person. I don't know my position. Say Radesh's position I know. Okay. And what's your name, please? Don't just sit down and say I made you something. Ishikito, right? Yeah. I will say Rai. Because in corporate world, they will go to, oh, Mr. Banerjee, Banerjee is like, with a task training. And they are playing cards, and they will, oh, Lari has come. Oh, Lari will come. So Ganguly is there. Ganguly will take Lari's task. I was in corporate world, they call by titles, not by names. So Rai is there, and Bad is there. Okay, Bad is there. Now, say you are the satellite. You are going around, right? And I am Sunando here standing. I know you the distance. You, Rai and Banerjee, they know their distance. It's around, say, 15 meters or 10 meters. But where I am in respect to Rai, I can go to that side, I can go to this side, anywhere. So, if this is Ishikto, then I am Sunando here. I don't know what my position. I can be anywhere. So I need the second satellite in form of Rajesh. Okay? So now I am a sphere around Rajesh. So now I have two spheres and they are merging in a circle. So now my position is defined. Defined a bit more. So I am not anywhere in that circle. So I need a third satellite. Who is you sitting there and saying, you have to shout like me. I can't hear.
Sir, Ohana.
So Ohana is the third satellite there. Okay. So I add. See, now after I get the distance from me to Ohana, this I I get 2 points. Either of the two. So I need another one. Okay. Another name can I have? আমার কানটা খারাপ নাকি বলটা খারাপ? তন্ময়. So I need তন্ময় to pinpoint at one of the 2 points. See. Yes. Done. Tন্ময় is well quite close, but it is not very far. Anyway, so I now know this is my point. Okay. That is the reason why you require at least 4 satellites. Right? At least 4. And you can also think of in the terms of simultaneous equations. I will just show you later. Okay. And there is called, now there is one thing which is very important, that it is, you have to have the clocks aligned extremely accurately. They are for cesium clocks inside, atomic clocks, and not your mobile. Actually, this clock, the GPS clocks are not displayed here, but in the case of when you see the GPS receivers, large and small receivers, they align their clock according to the cesium clocks inside the GPS, this space variables, we call SD, space variables, the satellites. So it is often said you can't have a more accurate clock than the GNSS clocks, okay, or the GPS clocks. Anyway, so now the question is the next time, and the more satellites you have, the better you can. Okay, it's just like this way. Pair of satellites in a distributed fashion.